Hi, good morning and welcome back to another round of Steel Connect webinar. So I'm Rocky and your host today to talk about steel and building related topics. So as usual, before we start, if you have any questions to ask during the webinar, feel free to drop it in the Q&A box on the screen, right? Also for those who are joining us in mobile, this is how you can navigate through the app to reach the Q&A box. All right, and as a fair reminder for fellow architects and engineers, if you wish to claim your LAM CPD points and BEM CPD hours, please stay through the entire webinar. I'll share the QR code and link of the survey form at the end of the webinar. And you may submit your LAM and BEM membership number via the survey form. All right, so without further ado, let's start our session today. So of course, today we are honored to welcome a guest speaker again. And the topic itself is called Beating the Heat, Assessing Solar Gain or Solar Heat Gain for Green Building Index. All right, so the topic itself will be covering green aspects of a building and understanding how solar heat gain and its strategies to score for GBI or Green Building Index points, right? And of course, you'll be understanding of how the overall building so-called thermal transmittance value can affect the energy usage, and also the roof U value calculation. And of course, delivering this topic today would be Architect Chan Xiong Ao. So I'm honored to have him on today's session as our guest speaker. So just a brief introduction of Architect Chan. So Architect Chan graduated with a bachelor degree in architecture and also master degree in architecture with distinction from Victoria University of Wellington, New Zealand. So he has more than 30 years of working experience as a professional architect and is the founder of his firm, Architect Dayaseni, or ADS in short. So as principal architect of ADS, he has completed high-rises, condos, hotels, shopping malls, and housing projects in Malaysia, China, Vietnam, and also Indonesia. So of course, aside from that, he actually actively contribute back to the community, also called the architect community, and became a president, PAN president, right, from 2013 to 2015. And he has also been appointed as a board member of the Board of Architects Malaysia in between 2011 to 2021. And Architect Chan was also the president of Malaysia Green Building Council in between the years 2018 to 2020. So without further ado, I would like to have Architect Chan on the screen. Architect Chan, good morning.
Okay, good morning, Rocky. Thank you for the invitation.
So I'll hand over to you. Yeah.
Okay, thank you first to Cindy and also to Rocky and BlueScope for the invitation to speak. Actually, I'm honored to share with all our fellow architects and engineers. Now, why is this important topic? Because it has now taken a standard MS 1525 and the significant 2684. I think the one for residential building has now become part of the uniform building bylaw already. Okay, part of the standard now become part of the uniform building bylaw under bylaw 38A, which was actually passed in 2012 under a federal law. Okay, so next slide. Okay, so why is climatic design very important? Because your design to climate is one of the first aspects of any green design. If you want to design in the tropical climate, I think all of you know, if you want to design here, you have to be competent in blocking out the direct heat from sunlight, because sunlight is one of the most major components in any design. So next slide. Okay, so the majority of architects design for the tropical climate based on their experience, their intuition, and of course the feel for the the climate that they are in. But I think if you look at intuition, intuition has its limitations. How far can you take it? Okay. So I think very important for us to remember is, as architects, we need to benchmark our design so that we are optimizing the design so that we reduce the amount of heat that goes into our building. Okay. That one you can actually calculate it. Okay. But then again, as architects, we need to, that there is a balance to any design. I mean, as you begin to get more experience in architecture and design, you will realize that you want to block out all the heat that outside from going into your building. Very, very easy. You put out all insulation and then no windows. Does that make sense? Doesn't make sense, isn't it? You need to balance somewhere, because when you put in windows, you actually ventilate the space inside your building, and also you allow daylight to come in. Now, daylight and ventilation, those are the two best natural things in life. Okay, so they help you to cool your building. At the same time, daylight actually is more energy efficient than all the artificial lighting you can think of. Okay, electric lighting is never better than direct daylight, but not direct sunlight. Okay, next slide. Okay, so we will go through very quickly bylaw 38A. What is its impact on us? Okay, now bylaw 38A, energy efficiency in buildings, actually takes MS 1525 into the bylaw already. So it states that if you are having a building, non-air air conditioned building, more than 4,000 square meter, you have to comply with MS 1525 OTTV, overall thermal transfer value. And then if it is more than 4,000 square meter, you have to provide an energy management system. These are the two things inside the bylaw. Okay. In addition, there is another part of it that says that you have to have your U value, or the thermal resistance of your roof cannot exceed 0.4 for lightweight roof and 0.6 for heavyweight roof. Okay, so this is the code of practice that is brought into the Uniform Building Bylaw. So next portion, next slide. So the building envelope. What is the building envelope? Is the external portion of the building through which the thermal energy is transferred into the building, and it is also affects the highest energy factor in any building, which is the air conditioning load, and of course the interior comfort of the building. Next next slide. Okay, so in order to understand what is the significance of the building envelope, we must understand two things. Thermal conductivity, that means how good is the material of your building envelope in allowing heat to enter your building. And of course the second factor is the thickness. So if you have a 3 meter thick wall, of course the resistance is very high, isn't it? But if you have a 3 meter thick steel, which is a high conduction value material, then the heat also can still very easily go in. So those are the two key things you need to know about building materials. First thing. Okay, next. So the other thing is you have to understand the configuration of buildings and how heat goes into your building. Now, typically, if you are a single-story terrace house, let's say you're talking terrace house, where is the heat actually going in? It is actually going in through your roof. Why? Because number one, the top surface of your building envelope is the one with the highest surface area. And also, if you talk about total heat impact on the surface, the top surface or the roof surface is the one that gets the most heat throughout the day. So you include the area plus the most heat. That's why single-story terrace houses 75% of the heat actually goes in through your roof. Whereas if you look at a double-story terrace house, it's 50% goes in through the two sides, back and front side, and then the top 50%. But by the time you come to a 5-story flat, only 40% actually comes in through the roof. Okay, next. Now, how about for high-rise buildings and commercial buildings? If you are looking at factories, 25% actually is only coming in from the side. Where is the rest of it coming in? Actually coming in through your roof. So if you have a single story factory, 75% of the heat is going in through your roof. That's why it is very important for you to insulate your roof, because you want to block out the heat, so that you have if you are aircon space, I think that 60% of the energy is from the aircon. And if you are using a non-aircon space, a naturally ventilated space, you want the working space to be a comfortable working space. So you want to insulate your roof to prevent heat from going in through your roof, especially for factories. Whereas we look at the low-rise building, the envelope, low-rise office building, for example, about 60% of the heat goes in through your envelope. Whereas for high-rise buildings, like high-rise office buildings or condos, 80% of the heat actually goes in through your building envelope. That's why it's very important to look at your OTTV value, okay, overall thermal transfer value. So in a typical Malaysian home, I think this one is, you can see why so much heat goes in through your roof. For example, in the different direction facing, like if you look at the north-south facing terrace houses, single story terrace, 86% goes in through your roof. Whereas the east-west facing one, you can see 75% going through the roof. Okay, so the rest are all numbers which you can I can derive. You can see for yourself. Anybody can calculate all these figures. Is available, or the data is available online based on Malaysian weather. Okay, next. So now, in order to comply with MS 1525, the latest version is 2019, I think, the latest one. OTTV applies to the building envelope, whereas the roof value applies to the roof only. So you have to differentiate the two sections. So MS 1525 got 3 sections. One is for the OTTV, the other is for the roof, and the third section is for the RTTV calculation. If you have a skylight, you need to calculate the heat coming in through the skylight, because as I explained to you earlier, the roof surface is the surface that receives the most amount of heat throughout the day. And if you put in skylights, I would say 80% of the heat will come in through the skylight. Okay, next. Now, I'm going to explain to you what is OTTV. This one, I think we don't have enough time in today's webinar to talk totally about the whole OTTV calculation. That one, if you want to know more, I would suggest you attend the Green Building Index. They run a seminar every quarter or every 3 months. You can register and take the first day course. The first day, they just talk about how you calculate the OTTV, because there are a lot of factors that come into the calculation. Now, bylaw 38 says your OTTV value or overall thermal transfer value should not exceed 50 watts per meter squared. Okay, so that one can be calculated. I show you a quick example. Next, we will look at of course, the assumptions is the envelope of the building is completely enclosed. It does not consider internal shading devices. That means if you have curtains inside the building, they are not included in the OTTV calculation, because by the time the sun shines in through your window, the heat already absorbed into the curtain already. So there's no way you can include that in the OTTV calculation. Okay, and solar reflectance or shading from adjacent buildings is also not included in the OTTV calculation, for a simple reason that today the building might be there, tomorrow it might be demolished, so you do not know. Okay, these are the things that we do not assume. Next. Okay, now OTTV consists, you see the formula at the top there, of 3 components. Okay, the first component is the heat conduction through the walls. Typically, this one, the brown color portion, in most typical buildings, it consists of between 0.2 2 to 5% of the total heat gain going in through the envelope. Okay. The second portion is the heat conduction to the windows. Okay, you can see this one here. 10 to 20% of the heat actually goes in through the conduction through the windows. The third portion is the one that's the most significant in tropical climates. Okay, now you look at the formula at the top, 194. That 194, that number actually applies only to Malaysia only, because it's a reflection of the Malaysian weather data. Okay, CF is actually now the new under the new 2019 version is called OF, or orientation factor already. No more CF already. They changed the wording already. Okay, the rest are all WWR. I think you all don't get confused with that one. It's not a worldwide wrestling thing. It is actually the window to wall ratio. That means wall conduction depends both on the area of the wall and also the thermal properties of the wall. Okay, so heat conduction through windows and solar heat gain through the windows. Now, this is where you have to be very mindful of. If your window area is quite large, it means a lot of heat going in through the windows. Okay, so it is in fact, if you have a building which is purely 100% glass, all glass building, you got to be careful about that one, because most of the heat will actually go in through there. 70 to 80% will go in through the glass of the window. Okay, next. Okay, I will explain this through one of the sample buildings, which this one actually was taken from the GBI facilitator course. My colleague, architect Won, was the one who prepared all this. I think his explanation is very, very clear. Carry on. I'll take you through one simple building lah. Okay, this is actually quite a simple building as an example. Next, let's see how we calculate the OTTV. Look, you see, what is window to wall ratio? Okay, window to wall ratio is simply the area of the glass you want to calculate, the wall area only. Okay, the wall area. So if it is if you're calculating the first portion, the brown one, next one, then you're taking the amount of area. So you can see this formula at the bottom there. 15 alpha. 15 is for Malaysian climate. Alpha is actually what's the color of your wall, because how much heat is reflected off the wall, multiply by the wall area. 1 minus WWR is just the wall area. And very important is the U value. The only thing you have control over actually is the U value and alpha. Those two things only. Okay. So if you have a very lightweight wall, you have maybe most of the heat reflected off. And the U value is actually the thermal resistance of the wall. Okay. The next factor will be the conduction through the windows. You notice here, now you're taking the WWR, which is the window area. Okay. So this one is the window area, multiply by the conduction value of your glass. Simple as that. So you notice this one is between 10 to 20% of the total heat gain. So a lot of people, they like to buy heavyweight glass so that they think that it actually helps them to prevent the heat going in. Actually, it's not a very important factor. That means you don't have to buy the people call high E value glass, E glass. That is for temperate climate, not for tropical climate, because this one is only contribute 10 to 20%. The one that's important is see the solar heat gain through the windows. Okay, next one. Okay, this one you can see the climatic factor is 194 here. Okay, orientation factor, different orientation, of course, got different amount of solar heat gain. Okay, the WWR is the window area, and the SC or shading coefficient. Now, shading coefficient got two components. One is the external factor. That means if you put in a lot of external shading, like horizontal shading, vertical shading, you can go to the MS1525 and estimate the amount of shading you have from the external factor, multiply by the shading coefficient number 2, which is the shading coefficient of the glass itself. Okay, so that's why when you select glass, for especially if you're talking about commercial buildings, it's very important for you to select the right type of shading coefficient. Typically, if you want the best value for money, it should be around 0.4 to to 0.45 to 0.65. That's the best value for money you can get. So instead of buying, like a lot of people like to specify double glazing. What does double glazing have? Actually, double glazing, you are doubling the cost of your installation because there's two pieces of glass you're paying for. And then the framing, the aluminum framing itself will double the cost of the framing. But you only reduce, let's say you reduce the thermal resistance of your double glazing by 50%. So if you are reducing that 50%, that heat conduction factor is only maximum 20%. So you reduce by 10% only. Whereas the shading coefficient, if you reduce that, this is a 0.8, no, 80%, if you reduce the shading coefficient, the SC here, of the glass, let's say you reduce it by 0.5, like SC is 0.5. Effectively, you're cutting the heat by 50%. So 0.8 times 80% times 0.5, how many is that? 40% of heat gain you reduce, compared to 10%, 40%, which is more valuable. Of course, it's the shading coefficient. And the shading coefficient glass is a lot cheaper. So you want to select the right type of glass. Don't go straight away think, oh, double glazing, double glazing. That one is for temperate climate. For tropical climate, the heat gain through the window is very important. So there's two things you can do. You can reduce the amount of glass you have in your window, okay, or you can reduce the shading coefficient. That means you cut down the SC value. SC value is the amount of heat actually going into the building. Okay, so when you have calculated the three portions, you can total it up. Then on the right hand side, you can see the total value of that one divided by the area of the envelope. Here 9245, you get the OTTV value. This one, I think, slightly above the 50 mark. So very easy. You just improve the SC value straight away. That one can go down already. Okay. So this is the key thing. Okay. Next. Okay. So how do you improve the OTTV value? You have to identify which are the largest contributor to the OTTV value. So the first one, of course, is the orientation factor or correction factor in the older version of the MS1525. The factor hasn't changed much. You go to table 4, you can see different orientation got different orientation factor. Is between 0.85 up to 0.95 or that sort of range. The second is your shading coefficient of your glass. Very important. This is where you can easily choose the right type of glass to reduce the shading coefficient. As I explained to you earlier, that is between the range of 0.45 to about 0.65. That's the best value range already. Okay, so if you are doing a high-rise building, no need to go and double glaze straight away. You can buy they call it laminated glass. One piece is shatterproof glass or whatever. The other is the one with a good shading coefficient. Okay. Now, the other is the external shading devices, which are given in table 5, 6, and 7, and the latest ones are all in graphical format already. Okay? In the 2019 version. Okay. And then the other is you have to review what they call the window to wall ratio, especially if you are doing like high-rise office buildings. If you want to have that look, the all glass look, nothing wrong with that. You can go ahead and do it. But the first 0.8 to 1 meter height from the floor up to that one, actually the daylight doesn't get into your building very much from that lower level. You are just allowing a lot of direct sunlight to go into your building. So what you can do actually, if you are, especially you are a tropical architect, always put a lightweight wall with insulation behind the glass. Okay, then you can paint it black. From outside, you can see it's still glass, but inside is already a wall already, because the lightweight material together with insulation has reduced your what they call window to wall ratio. Let's say if your window is 3 meters high, if I take away 1 meter, I already reduced by 1/3 amount of glass already. So the window area reduced by 1/3. Imagine that the 80%, 1/3 are reduced. 24% saving already, in energy bill on your building already. So together with your shading coefficient SC of the glass plus the window of the wall ratio, those two components already can reduce 60% of your heat gain into your building. So very important. Those are the key factors you have to attack those high value figures in your OTTV, especially you're doing for high rise building. Okay. These are the key things you got to remember. Don't go and attack all the wrong things. So in summary, the OTTV applies to the building envelope where the OTTV must be at no more than 50 watts per meter squared. And then your roof value thermal transmittance for lightweight roof cannot exceed 0.4. For heavyweight roof cannot exceed 0.6. So in terms of, say, if you are talking about, let's say, the thermal resistance, the total thermal resistance for a lightweight roof cannot exceed 2.49 meters per. The other one would be if you are having a heavyweight roof, cannot exceed 1.7, cannot be less than 1.7 for the thermal resistance. Okay, RTTV cannot exceed 25 if you have skylights in your roof. Okay, next. Next. Okay, now next I'm going to be talking about how you calculate the U value of your lightweight roof. I'm not going to be talking about the heavyweight roof because in Malaysia, a lot of there are a lot of low-rise buildings, especially like low-rise single-story factories, terrace houses, apartments, low-rise apartments, whereby they are using lightweight roof. Lightweight roof means either metal deck roof or tile roof. Okay. Now there has been a lot of confusion about how you actually calculate the U value of the lightweight roof, because a lot of people they think that I put a big air gap there. I take the value of the air resistance, multiply by the thickness, therefore I get a very high thermal resistant value. That's not quite right, because the minute your roof reaches a certain thickness, when the air gap beyond 125 mm of thickness, the thermal resistance will significantly drop. For what reason, I do not know, because this is research done by UKM and it has already been also shown in there. Now, recently, GBI has introduced what are known as RSI tables. RSI means actually is a resistance standard international in French. Okay, I think they are the ones who control. Now, if you are going to calculate the thermal resistance of your air gap, thermal resistance air gap, because when you use fall insulation, you have to fall back on this table. This table is actually available in the GBI website. Okay, it depends on few factors. Number one is your angle of your roof. You can see the angle on the left side there, and then the thickness of the air gap, and then the emissivity of your aluminium foil. This one, emissivity of 0.03 is the highest value of best type of aluminium foil already lah. If you go and buy the building paper with the sprayed on aluminium, or it's a vacuumized aluminium coating, the E value will drop easily to 0.10 or 0.09. So you have to refer to table A4 or A5 already. This is table A1. Okay. Now there are two tables inside the RSI table. One is the table A and table B. Now table B is where your air gap exceed 125 millimeter. Okay. Now, if you exceed 125 millimeter, the RSI value is given here already. Now, if your space is non-ventilated, you have to use, if it is reflective, that means if you got the aluminium foil on either facing down or facing up on it, you use the 1.09 figure. Whereas if it's ventilated, what do we mean by ventilated? Ventilated means here under ventilated, reflective one is 1.36. If there is only an air gap there, that means you've only got air only, got no aluminum foil, no nothing, you have to use a 0.46, okay, thermal resistance, okay. Whereas the non-ventilated one is 0.28 only, okay. So these are the 4 figures you can use from table B, okay. So I will go through several examples with you, okay. These are the values, UV and all that, okay. Let's go on. Next. I'll go through the first example with you. Okay, the first example is a metal deck roof with a foil insulation, number 4 on that figure there, number 4. It's a foil insulation with, like a fiber inside also, okay. And then it has a value of reflective value of, so it is the value of the insulation of the fiber alone is about 0.15, okay. Now, then you ask yourself, how do you actually determine the air gap value, the resistance, the air gap 25 and 75 mm? This is where you can refer to the RSI table, okay. This one I'm assuming is the best quality, 0.766 and 1.39. Okay, you can go back to this one here, RSI 3. You can see it's the 5 degree, the angle of the thing, angle 5 degree. You go down to the next, Rocky. Okay, you go down there. You can see the one 0.25 and 0.75, and then you see the figure coming out. 0.77, 0.766, 1.319. Those are the total thermal resistance value. Okay, let's go back to the roof and see, Rocky. Next. Okay, no. Okay, never mind. That's how we derive the value, okay. So you can see just now the earlier one, you can barely make it, because your total thermal resistance come up to about, I think 0.4, 2.48 or 2.49, around that figure where resistant. Therefore, you barely make the 0.4 U value. Okay. Now, the best is if you take a combination of both. You have you have a rock wool insulation or a solid insulation together with the fall there. Okay. So you can see the 50 mm mesh insulation gives you a total thermal resistance value of 1.38. Okay, 1.388. The 75 mm with the aluminum at the bottom there, it gives you a thermal resistance value of, you see the airspace there, 1.39. So those two values alone are already 2.6 something already. Okay, 2.6, almost 80% of the total thermal resistance already. So this one, you can see the thermal resistance is 2.959, way over the requirement for the MS1525, but it is of good value to you because it prevents the conduction of the heat gain and also the direct, they call it the radiant heat gain into your building. So this is the very good value. You can see this one easily will cover your cost of your, especially if you're using if you're using a metal deck. It is also recommended that you add in the mesh insulation, because the mesh insulation also help you to dampen the noise from rain if you are using a metal deck. Okay, next. Example number 3. Let's go to example number 3. Okay, this one you have a metal deck, okay, with only one single layer of one single layer of same the 5 degree, one single layer of radiant barrier there. Okay, this one got no foil at all, so therefore it's got no resistance at all. So there's 2 factors in there. Look at the 25 mm air gap, okay, because it's double-sided aluminum, and then the airspace is unventilated. It is, you can see it's 75. At 75 degree, if you move on further down to the right of the roof, it is already more than 125 mm already. So you have to use table B. Okay, use table B. You can go to table B. You can see it is IR reflected, non-ventilated 1.09. That's where we derive those figures. Okay, 1.09. So you add up those two, you can see the figure. It does not comply with the MS1525. Okay. Next slide, Rocky. Okay. Let's look at some some examples of tile roof now, because I think a lot of terrace houses and all, we still using tile roof. Typically it is normally up to about 30 degree lah, but let's assume it's only 20 degrees. The foil insulation emissivity best value already, okay, 0.3. You got enclosed airspace, so that's 20 degrees. So that one is you can see, you can use the 25 m, you can take from the table A1. Okay, the other one, you taken 75 m, take A1, you can see here 25 mm, 20 degree. Go on, next one. And you can go that's 25 mm, okay, 0.725 already. Next one, okay, 0.943. Okay, so this one is 75 mm airspace, because it's got 75. It hasn't gone to table B yet. Okay, so it hasn't gone to table B, therefore the air gap just barely make it 2.59 or 2.6 thermal resistant. So your U value is 0.39. So you can see there is a solid insulation together with the air gap and the foil insulation. So you can actually, now with the tile roof, you actually comply with the bylaw requirement. Next. Okay, now let's look at one roof, whereby you have only got foil insulation, got no solid insulation at all. Okay, and then the same air gap, I can see it's the same degree, everything. You can see everything else is the same, but the airspace there, 75 mm. You can see we are using, because it's unventilated, we are using 1.09 from the table B. Okay, table B, because the 6 there, you can see the 6 there, airspace unventilated. We are going to table B already. The minute we go to table B, you can see it cannot meet the requirement already. Okay, go next. Okay, so you can see the U value is 0, cannot meet the requirement. But if you ventilate the airspace, you can use the 1.36 value. Okay, it's attic space. That attic space, how do you actually ventilate it? Your air openings must be more than 1 to 600 of the total openings inside your roof. Okay, you have to calculate it properly. And or the other way of going around it is you put in a air extractor, those ventilator fans that you find on top of a lot of factories and private residences. So you put that in. Once you ventilate that space, then the U value of our thermal resistance of the airspace then goes up already. So you can see, you can actually meet the requirement already. You got the foil there, or what the attic airspace ventilated 1.36 together with the 0.725. So is you together with all the other components, you actually meet up with the requirement. You barely make it 2.5 okay, 2.48 or 2.5, you barely make it. Okay, so let's move on, Rocky. Okay, it's naturally ventilated, therefore it's 1.36. Earlier on we were using is non-ventilated, it's gone up to 1. It go down to 1.09 only. Next. I think that's about it already.
All right.
Okay, thank you very much. Pay attention.
Yeah, I was paying attention. Yeah, I hope our audience also. It's fine. All right. Thanks, Architect Chan, for the wonderful, insightful information. I hope our audience feel the same as well, and you learn a thing or two from here. So to our next session, it will be our dialogue session, where I'll pose my questions, the things that I think I need to ask and get it answered by Architect Chan. So to my first question, so just now you mentioned, right, there are two types of standards. One is for non-residential, which is MS1525, and the other one is MS2680, which is for residential building, right? So in terms of energy efficiency and usage of renewable energy for buildings. May I know what would be the major difference in between these two building code of practices? Yeah.
Okay. In terms of the code of practice, the first one is focusing on non-residential building. Second one is focuses on residential building. Essentially, they are codes of practice, but the MS 1525 is the one that is been taken and put into the bylaw 38A. Why? Because MS 2680, the method of calculating the OTTV and the RTTV and the U value of the roof, both of them, whether it's residential or non-residential, is the same. So inside of MS 2680, they also mention about the OTTV, but they refer to the method of calculation in MS 1525. That means even if you go to MS 2680, they don't repeat what is in MS 1525. They just say refer to MS 1525 for the method of calculation for the OTTV, the RTTV, and the U value of the roof. And the same standard apply for the residential and non-residential. So that means whether or not you are using, you're doing the roof for, a factory building, or you're doing the roof for a terrace house, the same standard applies, which is the one in MS 1525 for calculating the roof U value. Now, let me give you some advice. Some people, some artists, some architects, they have confusion about how to calculate the U value, how to calculate the OTTV. They don't want to go into it. Actually, if you don't want to calculate and you need certified value, you can actually write in direct to MGBC. They have a team there to help you. I think there's a small cost involved. Just pay them for it. They will do it for you. Okay. That one will help you when you get the certified value. Pass it to the local authority. You show you the that you have already got the actual value of your accepted RTTV or U value calculation for your roof. Okay. And OTTV also. Okay.
Thanks, Architect Chan. So if I want to renovate my house and improve the OTTV or RTTV of my terrace house, then yeah, I know where to look now. Thanks,
You
Architect
can go to MGBC to get help.
All right. Moving on to our next question. Yeah. Is about the calculation of RTTVs. Which suggests that the calculation is mainly looking at the thermal conduction through the roof, right? But my question is that do we know whether the RTTV itself also covers solar reflectance of
it
the
does.
material on the surface?
RTTV, it does cover the reflecting. If you have to go to the RTTV calculation. The RTTV calculation I did not show here today because it's a very complex calculation. A lot of engineers also get confused with that one. So don't include the architects inside there, even more confusing lah. Okay. So there is the same thing as the you saw the OTTV calculation. There's one, the solid roof, the opaque roof calculation. Then there is the opaque part. There is the alpha there. Okay, same in the RTTV also. There is one. Then there is the conduction through the glass, your skylight. Then there's conduction through your. But this is for ROTTV. RTTV, the formula is different. Okay, all the constants are different. In fact, constants are higher. And then the requirement for the roof is even higher. This one is 50. The other one is 25. Half of it. Effectively, if you take the RTTV calculation and take the solid portion, for lightweight roof, the requirement is 24. The U value, they got a constant factor of 24. Multiply by TEQ. I think this is quite a confusing. You effectively you have to have at least solar reflectance of at least more than 40%. Okay, I mean it has to be a value or not more than 0.45 or less. That means you have a highly reflective roof before you even start to look at the RTTV calculation. Better to use the U value calculation, which is the simpler method. That's what I showed you earlier. Go to that one. Don't go to the RTTV. RTTV a bit confusing lah. Not say confusing, a bit more difficult lah. You do it only if you have skylights. Okay. There is a requirement because of the 25. You see the constant factor of 24. You can barely meet it lah. So it's a tougher way of complying with the standard. Better to calculate the U value and just simply comply with that one. Okay, next one. Next question.
Yeah. Architect Chan, so that means if let's say you want to include skylight, then you need to calculate
yeah,
the
you have to
roof
calculate
to
the RTTV.
yeah,
The other
and
thing you have to remember is conduction for solid surface. That means not
metal
opaque
roof.
roof. Opaque roof.
Yeah.
If,
Yeah.
especially if you are talking about heavyweight roof or even lightweight roof, the conduction is the biggest factor. You know, the biggest factor there. And this is where you can see. I think measurements by I think Dr. Lim of UKM and also or Dr. Wong of National University of Singapore, they have been putting in metal probes and measuring the temperature of the rooftop. You know, typically at 12 noon in the afternoon or in later on in the afternoon, typically the temperature can range from between 52 degrees centigrade up to 58 degrees centigrade. It's as hot as that. Okay, and then imagine the heat conduction go into your triangular portion of your roof at the center there. That temperature can shoot up to about 45 to 48 degrees centigrade. So all the heat will go into your house if you don't insulate your roof. That's why it's important for you to insulate your roof, prevent heat from going into your building. Okay. Next.
In terms of the color, it may affect the temperature measurement as well, right?
Yes, because the higher the reflectance, usually the temperature will drop to about, let's say, like I said earlier, 40 instead of 58, maybe it will drop to 50, 51 like that in that region.
Okay, so it would so-called have the first
Yes.
shield against the OTTV or
Yeah,
RTTV,
because
I say.
but it only reflects they call it the radiant heat gain into the building, not the conduction heat gain. Still there, the conduction heat gain is still there. Okay.
All right, thanks. So yeah, about the question, because this always get asked, right? Yeah, is there a cost hurdle in going green? So if let's say I want to build a house, right, how much more should I fork out? For example, a terrace house, I think to be more specific, how much should I fork out to achieve the OTTV or RTTV figure that you just showed?
Okay, that one is by law already now. Okay, so whether you like it or not, you have to put in already the insulation. Either you put in the foil, which is the one that I showed you earlier. You want to meet the 0.4 requirement for lightweight roof, especially you're talking about metal deck. Either you put in you ventilate your roof, which is putting in the roto fans on top of the roof to ventilate your roof, or you put in double aluminum foil, 2 layers of aluminum foil, which will create the enclosed airspace with the proper ventilation, how do you call it? Proper air insulation requirements. Okay, that will bring you, that one is a solid insulation already. You go back to the one with so this is the best already. This is the best one for metal decking. If you go to the previous, okay, this is one 0.4, barely made it. Okay, 0.4. This one, both of them are using reflected foil insulation. You got if you put in a double layer, it will be the best lah. You know why this is very good? Because the foil alone is the highest quality foil. If you buy the cheap foil, you're not going to meet that requirement. Okay. And then also you can see the foil alone, also bubble foil, also maybe it's a bubble foil, already got its own thermal resistance already in there. So in terms of how actually if you're doing a double story terrace, how much extra does it cost to put in the insulation? In the early years, typical, let's say double story terrace house, the insulation, if you put in the aluminum foil plus the the solid insulation, typically one double story terrace house would cost around about 2,000 to 2,005. Now I think it's around 2,005 to 3,000 per house. Now, if you are staying in a double story terrace house and you switch on your aircon night before you go to bed, and then you leave it on, and then you run it for a few hours, or you if you stay in a terrace, sometimes people switch it off time it for 2 hours or 3 hours, then they by the time later on in the morning the temperature already dropped enough, they will automatically cut it off. So if you look at it, a typical double story terrace house, if you put in a 1 horsepower aircon, you are paying easily between $100 to $300 a month extra for every one aircon you put in there. Okay, so imagine if you were to put in the insulated roof, if you if your microclimate is quite nice, if you are staying outside the city center area, typically you will be using the aircon maybe instead of 30 days a month, you will use only 10 days a month or something like that. So you have already a saving of 20 days already. So imagine you are cutting down the thing to 1/3 of your thing. So instead of spending 300, you're spending $100 a month for the air conditioning load. That one, you multiply by 1 year is 1,002. Within 2 years, you already cover the cost of installing your aircon, not including the electricity bill. The rest is all earning already now. Okay, so it is in terms of return on investment. If you put in the insulation on your roof, it is within 2 years. Now, a lot of developers have this mistaken belief that in fact, I've talked to some developer who say, hey, I want to supply the aircon to the house buyer because aircon he can see, he switch on, he can feel coolness in his building. But then don't forget, he's paying between $100 to $300 more per month for that aircon electricity bill, no, and he's not helping the environment at all, no, because he's jacking up the electricity use. And where does the electricity come from? In Malaysia, it comes from your power station, and more than half of our power station are coal powered. So it just contribute more carbon to the atmosphere only. That's why number one, you are not contributing to the greening Malaysia. Number two, you're actually you're an energy guzzler. Okay. Now, if you put in the insulation, I think the ROI within 2 years you get back already. Okay. So roof insulation is important, but because of the understanding that the government has, they also put it into the bylaw already now. So that means whether you like it or not, you have to insulate your roof already. But if you have an existing building, it is worthwhile for you to insulate either by putting in extra layer of foil insulation, or you put in a solid insulation, rock wool or whatever, put it on top of your ceiling. If your ceiling can take the weight, put it on top of the ceiling. That will prevent the heat that's in the triangular portion, which I explained to you earlier. Measurements done have shown that it's typically between 40 to 48 degrees centigrade, about 45 degrees centigrade at peak at the center there. So if you are able to keep that portion from the heat from that portion from entering into your top floor of your building, it actually is significantly help you to keep your building cooler also. Okay.
Yeah. Thanks.
That answers the question regarding the return on your capital. Yes. I mean, it's one of the most worthwhile investment if you want to keep cool in your house, okay.
I do agree, Architect Chan, because I'm living a terrace house, right? And then I think my house was built I think more than 20 years ago. So understandably, it has no insulation inside the roof system, right? So whenever I because nowadays we have a choice of working from home and whatnot. So during the day when it's hot, especially now, I had to turn on the aircon to make sure it's workable in a comfortable working environment, So I do agree, and I think what you're saying is that the cost that they put in, even though it seems or sounds like it has the same cost as investing in a air conditioner, but in the long run, if let's say you're investing in the insulated roof, it is much more beneficial because you are not gaining so much heat inside the building, and by doing so you are using less energy in the long run, which can save you and hopefully buy you much more units of air conditioner in the future.
There's nothing wrong with buying air conditioner to put in your building because the climate is up and down one nowadays. Some days it's very hot, you need to switch on the aircon. But if you insulate your roof, actually you are reducing the number of times you need to switch on the aircon. A lot of time, if it is not hot, why switch on the aircon? Especially if you're microclimate, if you say you're living in the outskirts of city center, typically the outside temperature at night is less than 24 degrees centigrade. So it's between 26 to 24 like that. So sometimes if it is rainy day, it's definitely go below 24. So it's actually it's worth it to then you don't have to switch on the aircon actually. So because the microclimate itself is really cool enough already. Okay?
Yeah.
That's
Yeah. All right. Thanks, Architect Chan. So hence conclude our dialogue session, and then now we move on to the Q&A that is posted by our participants. So fair reminder for those who are who wants your questions answered, you have a questions that you wish Architect Chan can answer for you, please post it in our Q&A box. So currently I'm seeing 3 questions. I think one is from Catherine. So Architect Chan, let me read out the question, and then you can attempt to answer. So first from Catherine. So value of the bulk insulation, does it need to put in a Z spacer in? Can I use that value without Z spacer? I think what he's trying to say is that can I exclude the Z spacer in the calculation?
Yes, normally we don't get too carried away with that one. Spacer normally is not a big conductor lah. Okay, I think important is the ratio of the area, because even in your U value calculation, it's not actually very dead accurate. It's only an estimate, so it's good enough already. You don't have to include the spacer. Unless your spacer is very close to each other, then you need to include that lah. If not, not necessary. Okay.
All right. Thanks, Architect Chan. So, yeah, the next question by Catherine. Yeah, wait. Yeah, I think it's also the same thing. So, Jennifer is asking, can we ask to clarify using RO, RI, and RA when calculating the U value of roof build out? So RO is, I think, R outside, outdoor, R indoor, and RA. Yeah. So Jennifer, can you describe your question to be much more specific? So yeah, for anyone who wish to post their questions, again, you can go back to the Q&A box, and then we'll answer from there. So Jennifer, if you may further elaborate your question, then yeah, we'll get to that after. So I think yeah, I think what she meant, perhaps, if I may assume certain things, is that she's asking are outside the thermal resistance outside, the thermal resistance inside, and in between.
No, the thermal resistance is usually the one wall component, consists of either the roof is the tile at the outside, and then air gap, and then after that second air gap, third air gap, whatever you need to put in. So that's the U value calculation for the thermal resistance. Now, I want everybody to get a clearer understanding why the OTTV calculations are sometimes of more value than sometimes when you try to do building simulations. Sometimes when we use the electronic, we have a model of a building, then we run the simulation. That one, if you just do the thing for one day, for example, one day, you calculate the thing using an electronic calculation. So the heat gain from the one, how much radiation goes into a building, how much heat goes in, that's only for one moment in time. So you calculate for the whole day, let's say it's typical day, but then it doesn't take into account the weather situation or the climatic data for the whole day, for the whole year. That's why the OTTV calculations are important. The formula given is taken the average for the whole year. Whole year, and many years of data has put into the company to reach that particular data. So if you are doing just simulation, I take somebody's data and then to run the simulation, you have to run for the whole year, and you have to when you take that also, you don't know whether your weather data is accurate or correct or not. Whereas the one that's given in MS1525 is already done by the universities using significant Malaysian weather data over many years already. That's why it's important, especially the SC value and the OS orientation factor value. Orientation factor value and the SC value for external shading, all that is actually based on Malaysian weather data, not from any other place. Before the MS1525 came out, a lot of us used to calculate that based on foreign weather data. In fact, we used to depend on, there's one researcher called Dr. Nigel, I think he's from one of the roof manufacturer. He did research in, I think the data was from measurement in Rome, which is not, actually it's Mediterranean climate, not tropical climate, neither is it Malaysian climate. So it's a, it's a different type of climate. So this one, MS1525, is a Malaysian climate, Malaysian data. So that's why we in Malaysia we base on MS1525. So that data, of course, can be used in Singapore or Brunei, but outside that, I don't think it's relevant really. They have to establish their own constants and their own values. Similar in our RSI table, this is for Malaysian weather only, not for everybody. Okay.
All right. I think we have gotten Jennifer's clarification. Okay. Anyway, before we continue with the Q&A, for those architects who wants to submit your LAM or BM points, I mean your membership number, you can actually do that via the chat. There's a link posted by Clarence, so you can go there and submit if you have something else to do after this. But anyway, let's just continue the discussion. So Jennifer is asking, because this RORI is from the Singapore's document BCA. So architecture, do you have any understanding and cross-referencing between Singapore's terminology and how does it translate into a U value for roof build-up?
Singapore, they tend not to focus on the roof view value because the majority of their buildings are high-rise buildings. They also do not do a lot of research on roof insulation. So they don't have the published RSI values for their own roof also. So how they calculate, I'm not sure because I have not seen the thing. Although I've taken their, the standards, their green building, their green building courses in Singapore. They do, even their OTTV and RTTV calculation are different from us because the method they use is sometimes I don't totally agree with their assumption. They might be correct for their use, but for Malaysian use, it's better for us to go back on our own OTTV calculation. Like as I said, ours is based on Malaysian climatic condition and Malaysian type of construction, not from Singapore type of construction. So Singapore one, if you are doing work in Singapore, you have to follow their bylaw and their standards. Malaysia, we follow Malaysian standard Okay.
Yep. So I think to answer to Jennifer, so we have no answer for you. If
I don't have an exact answer because I don't want to answer off the cuff and say it's how they derive that value it's different from us.
Yeah, perhaps so Jennifer, you can refer back to the document, the BCA document in Singapore. All right. So moving on to the next question by Jason. The question is, can we design a ventilated void in between the roof level and the ceiling so that the temperature can be reduced?
This is where you can either, especially you're talking about the triangular portion of the roof, the triangle portion that is between the tile
attics.
roof or metal deck roof, the attic area there. The best thing is, if you want to do that is, you need to put in the fall insulation, because then it's a reflective space. Then you go back to the table B, which I showed earlier on in the RSI. Table B for ventilated and unventilated, there's a big difference. When you ventilate means during the afternoon, that heated air that's inside there is then released out. Okay, so you can either put in a ventilator fan which sucks out the air, and then there's no electricity or motor running it. It's just a natural ventilation to it, and there is a sufficient, or at the end there, the two ends maybe you can put in those louvers to allow air to flow right through your attic area. Then that would actually then be considered a ventilated airspace, but you still need to put in that aluminum foil to make it a reflected aluminum ventilation space, because measurement already done by Dr. Lim of UKM show that when you start to make the gap bigger or smaller, and when you measure different types of roof, you have different outcomes. You sometimes, a lot of time, when you try to do scientific simulation or measurement, you do not know whether it's accurate or correct, because sometimes you might have missed out certain how they call it, factors. Maybe Rocky, we will go back to the other one earlier on, that just off the cuff. You show the one that I was talking to you about earlier, and the one that Dr. Lim's research. Next one, you show those one. I will quickly go through with you about how we arrive at the latest RSI tables. Okay, this is the one that is the bubble foil. I think Rocky, you show the front part of the one whereby they have the report. I mean, in that one, although we don't show you the one. Okay, next one, you go and see. The report done by this one. Before that, there's one with the header itself. You can see. These are different type of foil. This is the method of measuring the thermal resistance of your foil and your material. Okay, the latest MS 2095 updated one already allow only if you are a manufacturer, okay. Now they only allow the measurement taken from a heat flow meter, no more from the heat plate already. Previously, before these few years, measurement of the value of your foil, your thermal resistance of your foil value, they can use a heat plate, because the heat plate takes a long time, a few hours to stabilize the temperature before they can allow the acceptance value of the thermal resistance. So a heat flow meter, very fast, within 1 hour they can already stabilize and measure already. Okay, next you go on and see. That's what I showed you earlier already. And then a lot of times when you do research like this, carry on, Rocky, move on. See, okay, these are the value you can see. When the air gap get bigger and bigger, the thermal resistance actually doesn't get better and better. It starts to drop off one. Okay, this is from Dr. Lim's research, bubble foil measurements. You can see on the right hand side, it gets thicker and thicker. The air gap get bigger, the thermal resistance starts to drop, not go up. Okay, so there is a limit to it one. That's why we have table A and table B. Okay, next. You just measure in the measurement. They call it the heat flow meter. Is not enough. Sometimes you have to do a field measurement to measure this. This is done by Dr. Lim in Malacca, Center of Peninsular Malaysia. All the standard one, you got a control building, then you put in the different type of roof, different type of insulation, then they tally back that measurement to the one that you do measurement in the heat flow meter before you allow the figure to become a finalized figure. because then like I said, no, these are empirical measurements you need to do before you can actually put out the tables that we were talking about lah. Okay, so I hope that there is some understanding that the RSI table didn't come from other places, but actually measurement done, a lot of hard work and measurement done by our local universities, and also of course that all that research work has to be sponsored by somebody lah, and that was actually sponsored by Green Building Index. Green Building Index, whatever money they so-called make from it actually contribute towards all that research. You need to buy equipment for the research. You need to put up all those research huts and things like that. All that need money. See, so this is where GBI has actually contributed research money into this. This type of research, I think Singapore don't do it because you know why? They are all high-rise building. Okay, they are all high-rise building. They don't worry about their roof insulation, because for us we have a lot of low-rise building. We have low-rise factory. All that have very big significant roof area. And imagine I already showed you earlier on, most of the heat for single-story buildings actually coming through the heat. Okay. Logan says what is it? Okay.
All right.
RWHS only apply for semi-D and bungalow. What is RWHS? Rainwater harvesting system.
Wait. Okay. Architect Chan. So I think to answer to Jason as a summary for Jason, it would be that it is possible to so-called ventilate the void in between the roof and the ceiling to reduce the temperature down. I think just now Architect Chan, you have shared some examples on how to actually do that, and in essence, that would, I mean, if let's say you want to translate that into a much more tangible calculation, then refer to the RSI table, or rather the table B lah.
Yes, table B.
For
table
the,
B is
for
the
the
one
number,
that give you
to get a much more quantitative number for you to use. All right, so I would move on to the next person. So Eric. So Eric asked, is there any recommended single skin roof system without plaster board but achieve U value 0.4?
I think I did show you example 1, isn't it? That one exactly 0.4. Without the plaster board, I think you need at least I would recommend if you want to do that, you put 2 layers of bubble foil in there, and then you actually already achieve that already. 2 layers of double foil.
But I think it has to consider the RSI value as well, right?
Yeah. Two will give you 3 spaces, 3 air gaps already. So that would be the best one. If you want to do without the how do you call it? Without the solid insulation. But solid insulation is always recommended for metal deck roof, because you don't want the sometimes it's raining, you don't want the
sound.
The sound from the rain to go into your spaces. And solid insulation normally also acts as a sound barrier, in addition to being a heat barrier also. So you double value for your solid insulation.
All right. So to Eric, the answer is is possible. So it's just depending on the combination of the components.
Yeah. The combination is actually infinite. So it's you need to actually put in the calculation in order to know. Like as I said right from the beginning, you cannot use your intuition. Agak get the figure. You still need to go and calculate. That's why sometimes I say architects. I'm an architect. Sometimes in the beginning also very lazy or don't like to do maths. But now have to go back and do some maths and science already. We have to depend on benchmarking a better value for our architecture. Okay.
Okay. So the next question is, I think it's a statement, but I think maybe Architect Chan, you can share your perspective. It's from Joachim. So the question is calculations considering thermal bridging and without considering thermal bridging between it makes a big difference in his experience in calculating the U value of a roof system. So I think what he's trying to say is that the Z spacer, just now, Architect Chan, you mentioned can be neglected, right? So, but in his statement, he said, without neglecting the Z spacer, would make a big difference for the U value. So yeah, any perspective from your side, Architect?
So it depends on what is your spacing lah. If your Z spacer is using metal then in a very high conduction value, I think then it would be wise to include that into your total calculation of your R value of your so-called roof lah. But a lot of times the air gap they don't have that one. If it's using like for example you're doing tile roof and you're using say timber spacing the timber is so thick already. I don't think it's a significant value on your total bridging lah. If you have metal, then you need to consider it lah. Okay, but even if you're doing metal, a lot of times the spacing is quite far apart lah. So I wouldn't say you need to include it in lah. If you want to be dead accurate, then of course include it in lah. If not, I think a lot of times people excuse you from it lah. They let you you off lah. Okay.
It's just a matter of how detailed you want the value to be. Yeah. All right. So hope that gives you a different perspective. So yeah. So
any other questions?
Okay, so yeah, got from Param. So the question is tile roof. Does it fall under lightweight or heavyweight roof?
Lightweight. Tile roofs under lightweight.
Okay. Because I think
heavyweight is actually under MS 1525 2019 version. They don't talk about lightweight and heavyweight anymore. There is concrete roof and non-concrete roof already. So if you are using a concrete roof deck, that one is come under the heavyweight roof already. So that one is 0.6 for U value, and your thermal resistance cannot be less than 1.7. Okay, whereas the thermal resistance for lightweight roof or tile roof is 2.49 or 2.5. Normally, that's the region we are talking about. Okay.
Yeah, but okay, Architect Chan, further to Param question, because I noticed in the previous revision of MS 1525, they did classify what is considered lightweight roof by kilograms per meter square. So I think if let's say anything above,
it still applies lah, but that is the older version. The newer version, they don't want to confuse anybody anymore. They just say concrete roof or non-concrete roof. But if you are using concrete roof, definitely you will exceed the figures given in the 2007 version. Okay.
Okay. All right. So the next question is okay, why is R value of bubble foil higher than rock? Example, we even saw a bubble foil brochure stating that the R value of more than 2 would, have you seen such statement in any brochures, Architect Chan?
To be honest, I not seen it yet, but their claim, whatever they claim, need to be confirmed by either CRIM or any of the approved laboratory. Otherwise, they simply put in the figure, they cannot. Then they have to state the condition in which they arrive at 2.0. Is it just the bubble foil itself, or the air gap above and below the bubble fall, or is it just one air gap only? So it depends on the air gap, and the air gap thermal resistance, as I explained to you earlier. I think Rocky, you also understand after we go through the 4 or 7 examples that aluminum foil insulation thermal resistance depend very much on the air gap and the emissivity of the material of the foil, plus the angle of the roof. Those 3 factors must come into consideration. Okay, and then the air gap, when it gets too big, also become not help really at all. So it starts to drop, the thermal resistance drop. So that figure given by the bubble foil manufacturer need to clarify clearly whether it's double-sided aluminum foil, which has got air gap above and below, or only the bubble foil itself. If you ask me, bubble foil itself to get 2.0 a little bit tough lah.
Okay. So the next question is by Joe Kim again. So I think yeah, the question, if I may translate, would be sometimes, I mean, I think yeah, the test method for I'll just try and read out first lah. The test method for thermal resistance R value for foil had a air cavity below and above the foil, which seems to provide a misleading R value as the air cavities are also considered in the testing. How do we use these values in practical calculation? So I think my understanding of this question is that the familiarity of your foil above and below, how do we actually know that it is realistic in actual practice? So architecture, maybe you can share perspective of why is there R value in between the air cavity or air gap as you refer it to?
Because the air itself has got thermal resistance, that's why it's got the. But that thermal resistance depends on the reflectivity of the foil itself, Okay, so if you have a non-reflective, that means you put building paper, okay, building paper only, then the air gap actually has very little thermal resistance. Because I don't know why. This is all measured values. Okay, these are measured values using the heat flow meter and also the one you see, those little houses that he's been doing the experiment on. Those are all empirical values. They are measured values. Okay, not from simple calculation. Sometimes you do simple calculation. As I explained earlier, when you're talking about the weather, there are a lot of factors inside one. You do not know what you missed out sometimes when you do as computer simulation. So the one that you did not include might be the one most important factor. So you do not know. That's why in the case of the foil insulation, it's been taken so many years for them to run for experiment after experiment to come up with the RSI tables that we are already using right now. Okay, that's why it's there. Those are empirical measurements. I do. If you want to ask me how and why, I'm not the scientist doing the research. They are the ones doing the research. Maybe one of these days, Roscoe might invite Dr. Lim to come in and explain about his experiment, because that one is, as far as I understand, he is still running research on the roof metal decking also for different type of angle and different type of the alpha factor, the color and all that. And then he's doing a control lab now. He's not, sometimes you put those type of, the 3 little houses that he has got all over in, one in Malacca, one in UKM itself. The data sometimes get very, very frustrating because it's weather data
cannot
is
be repeated.
No, cannot be repeated. So scientists, when they cannot repeat when other people say you do this, and then he tried to repeat that time, you get a different figure. They say, they spill your figure and things like that. So quite difficult, I would say. So to standardize matter, you need to take long-term measurements. So sometimes they measure over long-term. Then he's got a lab also in a control environment also to do that one. So control environment versus they want to measure the confirmed theories. The other is the actually empirical data which you do measurement at the site itself.
All right. Yeah, thanks, Architect Chan, to share the perspective. So, in essence, I would understand it as the R value of the air cavity is going to sound useless if, let's say, you don't consider those factors, such as, I think in the experiments they run in between different roof
angles,
pitch, different
different
air space,
different air spaces,
yeah,
and different emissivity of the foil itself. So those three key factors, you see, emissivity of the foil, the angle of the roof, and then the size of the air gap. So you can see the table is quite big table. They've been measuring one after another, and then when they stabilize the thing at the site measurement, at the heat flow meter, they then go back to the site and confirm at their little huts there whether or not the two figures tally also before they come up with the RSI tables.
All right. All right. Thanks, Architect Chan, for the perspective. So we have our last question, which after this, then we'll conclude today's session. All right. So the last question is, does GBI provide green certificate for products listed in green pages?
No, the green pages is actually similar to the yellow pages, but only for green products. If you want to list as a product, a green product. But if you want, if your product is, if it is not within inverted comma, not green, or you don't have any accepted lab test to prove your data, you can only go in as an advertisement or within inverted comma, advertisement lah, not as a product data sheet lah. A product data sheet, you need to have test result from a recognized laboratory, and that is under the Malaysia Green Building Council, not under the GBI. GBI is only a rating body. So I think for those who are either developer or not developer, maybe house owner, I think GBI is also working on coming out with existing building rating tool for residential buildings. So that means if you want to see where you stand, how green is my home? You can go down. I think they are going to upload it quite soon, as soon as they get it. I think they're still at the development stage. One that is ready, you don't want any certificate. You just want to know where you stand. Okay, you can go down, you fill in the data, you can get okay, my GBI value for my house is 50, 100, 90, 80 or whatever lah, the figure you get lah. But if you want that to be verified, means somebody will check whether or not you put in the data correct or not. You pay a small fee lah, just like if you go and drive the motorcycle in the kampong, nobody is going to stop you, But if you want to get a license to ride the motorcycle on a legal road, you need to do a test, Similarly, GBI likely to have this type of test for you. You pay a small fee, then you get your certified green building for your green building index value for your home.
All right, thanks, Architect Chan. So to give you a short answer, I would say GBI is not a certification body, so they cannot give you a green certificate.
Not for products.
Yeah, only not for products. Building. Yes, for only
products.
For building.
You got to go back. Go back to MGBC. Because MGBC has got professional members. They have got industry members. A lot of manufacturers of green products actually are members of MGBC because they want to promote their product for the green industry. So they join the MGBC as an industry partner.
Yeah. All right. So and the green pages itself is basically a product listing. So
Yeah, it's a product
more of
listing
a
for green products. Yeah.
mhm,
For example, BioBricks, they are a member. They are also they have their data sheet. They call it a data sheet for their
mhm,
BioBricks.
mhm. All right. So hope that clarifies the difference. All right. So to conclude today's session, I would like to summarize it in such a way. So the topic was beating the heat, assessing solar gain for green building index. So from Architect Chan's insightful sharing, I think I myself have understood the importance of solar heat gain and how it may affect the energy usage of a building in the long run. Okay, and I think the example shown in the sessions itself also suggested that there are many ways we can achieve a green building to meet the requirements, and especially for the roof, right? Different configuration that Architect Chan have shown, and also and what I took from here is also that the color of the building or even the roof itself can affect the calculation of OTTV and RTTV. And I believe from here, our participants can actually be much more confident in, investing in, building that is greener, and especially for developers to see the difference in between buying either to prioritize on buying an air conditioner or insulating the roof. I think Architect Chan, you have shown a very clear example and also explained, why is it much more beneficial to, insulating the roof to have a better RTTV. Okay, so I think overall, the essence is that it's not just a green building in terms of RTTV and OTTV. It's not just going to be beneficial for the environment perspective, but financial sense it also makes a lot of sense right now, right, to actually achieve that. All right.
Yeah.
So with that, thank you, Architect Chan, for today's sharing, and
Thank
also your
you
expertise is
to Rocky. Thank you
invaluable.
to you, Rocky, and Cindy also, and also
Yeah.
to BlueScope lah for the giving me the opportunity to share my experience on green buildings with the architects, engineers, and also whoever are in the building industry in Malaysia. Thank you very much.
All right. So
Yep.
yeah. So this is a promotion of our session. So if you have any ideas or interesting design projects that you think is worthy or you want to share it more broadly, why not share it here, right? So feel free to email us via email events@bluescope.com to get in contact with us, and then we can talk from there. All right. So of course, for those architects or engineers who are still on the channel, so you can scan the QR code on the screen to submit the survey. It's a survey form, and you can submit your LAM or BM membership number inside the survey form, and we'll get to registering it for you. So of course, if you enjoyed the session or think it can be improved further, do share your view in the survey form as well. So I'll leave the QR code here for a few minutes, and after that, we shall, end the session. Actually end the session without sharing the screen. All right. So with that, I would like to thank everyone for your participation. Okay. All right. Have a good day and bye.